Hey guys, welcome back. Today we're going to be continuing our discussion on Unit 1.2, Chemistry and Living Systems. Today we're going to focus on Part 3 notes, which is on acids and bases. All right, so you guys ready? Let's dive into this. So first off, let me move this. There we go. So water is neutral. What we mean by that is that it's neither an acid nor a base. So what does that mean again? Water rarely forms ions. When it's in its liquid form, it doesn't want to break apart. So remember, the structural formula for water is H2O, and it does not want to break apart into a hydroxide ion, which is OH minus, and a hydrogen ion, H plus. So it doesn't really want to break apart. And even when it does, those ions balance each other out because it's H2O. So one H and then oxygen and H. So we still have H2O. So they balance each other out. So water really does not want to form an ion or break apart to form ions, but even when it does, even though it's rare, when it does, the ions cancel and balance each other out. So that's why we say water is neutral, and that means that it's neither acidic nor is it basic. We've heard of terms like acids before. You might have heard terms bases, not like baseball bases. But we've seen movies and TV shows where they talk about acids, and that's kind of what we're talking about now. There are certain substances that are considered acidic. They are acids, and there are other substances that are opposite that, which are bases, also known as alkalis. So question becomes then, how do we measure if something is basic or acidic? And what we do is actually just look at the concentration of ions, specifically hydrogen ions. And we've taken this and put it into a logarithmic scale that we call the pH scale. We'll actually show you some examples of those and help you to understand what we're talking about in terms of the ions and acidic and basic natures. Yeah, crazy. Might be best down there, we'll find out. So the pH scale, as we've mentioned, this is a logarithmic scale that helps us to look at the amount of different ions, specifically hydrogen ions. The scale goes from 0 to 14, and water is right smack dab in the middle at 7. So pure water, pure H2O, is a pH of 7, meaning that since it's right smack dab in the middle, that it is neutral. So right here, you'd see in the picture, water is right smack dab in the middle and is considered neutral. If the value is below 7, so 0 to about 6.5, then it is considered, the substance is considered an acid. It is more acidic. If it's above 7, let's say about 7.5 to 8, all the way up to 14, that substance is considered a base. It has basic quality or properties. And as you can kind of see on this map or this diagram, milk is just slightly acidic, still kind of on the neutral end. Bananas have a pH of about 4.8, tomatoes a pH of 4, apples have a pH of about 3.2, vinegar is about 2.8, give or take, lemons have a pH of 2, and then all the way at the end, we have hydrochloric acid. Now, what you might notice is, I'm hoping some of you are thinking, milk is an acid, bananas are acids, and yeah, and again, it just kind of boils down to the idea of or ions, making hydrogen ions. Now, the closer you are to 7, the weaker an acid you are. The farther away, the stronger the acid. So lemons, you know, you kind of get that like tart, stingy feeling when you bite into one. That's because of the acid that's in there. It's not enough to harm your mouth or anything like that, but it's still a pretty strong acid. The strongest, though, all the way at the end, usually between 1 and 2. You don't really want to mess with those. Those are the hardcore acids. They are burn right through you acids. Not good. So the closer you are to 7, the weaker an acid. The farther away you get from 7, the stronger an acid you are. On the other hand, here we have bases. And it's the same idea. The closer you are to 7, the weaker of a base you are. So we have blood is somewhere around 7.5. Baking soda is around 8.5. Soap, we use soap all the time, hopefully. And that has a pH of 10. Ammonia, which is a type of cleaning solution, has a pH of 11.5. And then all the way at the end, drain cleaner has a pH of 14. That's why it's very, very caustic, and why the label always says, you know, if you get it on your skin, rinse it right away. If it gets in your eyes, go to the emergency room, because it is a very, very strong base. So this is looking at, once again, the strength of the base. So the closer it is to 7, the weaker of a base it is. But the farther away you get, the stronger it becomes. All right, let's take a look at our picture. So this is just another picture to kind of put it in terms of other effects. So this is looking at the pH of a lake, and it can kind of tells you a little bit more about some of the, on the right-hand side, some examples of substances with that pH. And on the left-hand side, it shows you some examples that could happen in terms of what happens when the pH of a lake changes. So again, 7, pure water. Now, a lake, no lake is going to have pure water. When we talk about pure water, we're talking about just H2O. But there's always going to be other sediments, minerals, anything like that within a lake, so that's going to affect its pH. Milk says is about 6.5 to 6.8. A healthy lake is around a pH of 6.5, so it's slightly acidic, and that's just mostly because of, again, all the living organic material. pH of 6. So remember, healthy lake is 6.5. When you get to 6, that's when rainbow trout begin to die. So we're starting to see negative effects. It's actually just that 0.5 range is enough to cause entire species to die out. Clean rain is 5.6. Now, at 5.5, just slightly below that, we have frog eggs, tadpoles, crayfish, and mayflies all die off. So that's the point where it's too acidic for them. They can no longer survive in that lake. Bananas are between 5 and 5.3 in terms of pH. An acidic lake is at about 4.5. Acid rain is between 4.2 and 4.4. At 4.2, that is when all fish in that lake die off. They are gone. pH of 3, orange juice or soda. pH of 2, lemon juice, vinegar. pH of 1, sulfuric acid. pH 0, battery acid. Now let's look in the opposite direction. You don't necessarily see a whole lot of environmental effects, and that doesn't mean that there won't be any. It's just more so because of increases in certain compounds in the air. We tend to see more acidic effects like acid rain running off into lakes, causing then the pH in the lake to rise, and that's why we see these effects with lower pH. You would still see negative effects if the pH got too high, meaning it was too basic, but we just generally don't see that because there's not a whole lot of these things being added to lakes, if that makes sense. So seawater and eggs are about at a pH of 8, baking soda, pH of 9, milk of magnesia, pH of 10, ammonia, pH of 11, soapy water, pH 12, bleach, pH 13, and liquid drain cleaner, pH 14. Okay, let's talk a little bit about properties of acids. So, an acid is a compound that will form hydrogen ions in solution. So that means that when you add it to water and form a solution, it's going to break apart, and one of the things that's going to break into are hydrogen ions. So here's an example. We have hydrochloric acid, HCl. When it breaks apart, it becomes H+, so that's a hydrogen ion, and Cl-, so that's the chloride chlorine ion. But notice we have this hydrogen ion right here. The more acidic it is, the more hydrogen ions you would get. So it's increasing the hydrogen ions. Some things you would notice about it, if you had blue litmus paper, there's a litmus paper test where you have blue litmus paper and red litmus paper. Acids will not affect red litmus paper, but they will affect blue litmus paper. They will turn the blue litmus paper red. They also tend to be sour tasting, kind of have that tingling feeling on your skin or on your mouth, almost a burning sensation. So that's why like lemons or oranges, why when you bite into them, they kind of tingle your mouth a bit. It's because of the acids within them. So properties of bases. A base is a compound that will form hydroxide ions, OH- in solution. So here's an example. We have sodium hydroxide, NaOH. When we take the NaOH and we break it apart, we get Na+, that's a sodium ion, plus OH-, that's the hydroxide ion. So what happens is in a base, when it's added to water to form a solution, you're going to see an increase in OH ions, the hydroxide ions. Now, some of these could bond with existing hydrogen ions, which is going to cause the hydrogen ions to decrease, and we still have more hydroxide ions being added. So the hydrogen ions decrease and the hydroxide ions will still continue to increase. These tend to feel more slimy or soapy, and they also tend to have a very bitter flavor. So if you've kind of ever accidentally had soap in your mouth, it's not so much like that sour, tangy, like, it's more like, it just tastes nasty. So that very, very bitter flavor. Again, going back to the litmus paper test, it will have, bases have no effect on blue litmus paper, but they will turn red litmus paper blue. So again, we're seeing the opposite effects that we saw with acids. Let's see. You might also notice that a lot of things we talked about in terms of bases, they're cleaning products like soap, soapy water, ammonia, drain cleaner, detergents. All of those are bases. And the reason why that is, we're actually going to talk about in a moment, is because of how they relate to us as living things, which again, we're going to talk about that in a moment, but just take my word until we get to this very next slide. So neutralization, let me move my camera a little bit more. There we go. So neutralization, how do we neutralize an acid and a base? Well, since acids increase hydrogen ions and bases will decrease them by forming hydroxide ions. So acids increase hydrogen ions, bases increase hydroxide ions. We have H+, OH-, they balance and cancel each other out, and we actually get water as a result. So what happens is, I don't know why the little equal sign didn't show up. I apologize for that. Sometimes weird things occur when I go from PowerPoint to Prezi. So HCl plus sodium hydroxide, so that's an acid plus a base, the products we can see will make sodium chloride plus water. Now we show that right here. HCl plus NaOH. Now what occurs is, remember we said an acid is going to break apart to form hydroxide ion and the other components. So H plus and Cl minus. Same with the base, sodium hydroxide. It's going to break apart to form a sodium ion and a hydroxide OH minus ion. Well, what happens with that is the hydrogen, the H plus, and the hydroxide OH minus will bond to form water. And then the other two ions will bond to form some kind of salt. So Na plus will bond with Cl minus to form sodium chloride, table salt. Not all salt is edible. Not all salt is table salt. For instance, the rock salt that you put outside to, in winter to melt ice, don't eat that. Yes, it is a kind of salt. No, it's not edible. It's poisonous. Here's another example. We have HNO3 KOH. So we break that apart. We get a hydrogen ion, H plus, and a hydroxide, OH minus, and those will bond to form water. Then we're left with K plus, K is potassium, and NO3 minus, and we get KNO3. So that's a type of salt. Not table salt, don't eat it. So when you have an acid and a base, you can actually neutralize them by mixing them together. However, this only occurs if they are of similar strength. Because remember we said that weaker ones will give off less ions, stronger ones will give off more ions. And the point of this to neutralize is to take all of those ions and cancel them out. So we want to cancel out all of the hydrogen ions with hydroxide ions in order to form water. So that's how you neutralize an acid or a base. So if you have a strong acid, you neutralize it by adding a strong base. If you have a weak acid, you neutralize it by adding a weak base. And the products will be water, H2O, plus some kind of salt. All right, some additional resources. We have one resource from me in Science in Pajamas. I do some demonstrations on acids and bases. We do a blue litmus paper test. I didn't have red litmus paper at the time. I apologize. We also do tests with pH paper in order to show you the strength of the different product or substances. So that might be a good one for you to check out. I also have some other videos to help you out. Ricochet Science, which has one on acids, bases, and pH. Another good example, good explanations. Don't Memorize, which has one on acids, bases, and salts. This is an interesting and really good series that I've just found out about. Might be a good one for you to check out. And then also one from Don't Memorize on neutralization. So again, good videos, check them out. If you have questions or not quite sure, you just kind of want to go into more detail. But in the meantime, you guys, don't forget, well, first I'll post the link for the Prezi into the description so you have access to the video links. Hi, Ripley. Don't mind him. But in the meantime, you guys, just stay awesome, stay curious, and most importantly, stay safe and healthy. All right, you guys, take care. Bye-bye.